Yeah. Okay, so let's go ahead and get started with the lecture. It should be a fairly quick lecture. I don't think it's going to take much time.
So is this SW5 like?
Yeah.
Okay.
Yeah, after today's talk, you should be able to do software number 5. Okay, before I forget, always bring bugs after a test. Before I forget, and I put this in the same email when I corrected the, the scoring for the exam. Next class, right? So Thursday, and that's going to be the first lecture on the control unit. So really important lecture. I mean, all the lectures are important, but control unit, both lectures, really important because that's probably the most challenging piece of hardware that you have to design. And at the beginning of Thursday's class, so just like the exam started at 8:10, after my little spiel, there's a graded in-class activity Thursday, and it's at the beginning of the class. The last activity was, after I lectured. But this activity is at the beginning, so you need to be here at the beginning, just like everybody was today. I'm very impressed that everybody was on time. I think that's the first time that's happened in I don't know how long for an 8 to 11 class. So if you can do it for an exam, you can do it for every lecture. You should be able to. Okay, so on each table, I put the page from the assembly language manual that has the information about the reg file registers, because we're going to briefly go over some of the things that are on that page. And then we're going to talk about assembler directives. And then after that, we can talk about how you essentially put data into the data segment of the real memory. Okay, because remember how we said that in real memory you have these 3 segments. There's the code segment, the data segment, and then the stack. And what do we have in the code segment? Right, that's where the instructions are at, right? But we haven't really talked about data stack yet. Today we're talking about, this segment of the real memory. And then the last lecture of the quarter in a couple of weeks, that's going to be part of that lecture is dealing with what the stack segment is all about. Okay. And, just like the code segment is byte addressable, all these other segments of real memory, right? The data and also the stack segments, they're also byte addressable. Okay. Do you recall, or can you find out if you don't recall, where the data segment starts? Because our code segment starts at all zeros. Yeah, that's all zeros. Do you remember how far up an address the code segment goes? Right. You got it. Very good. Well, all zeros and then 5. Like that. So the first address of data segment, the first address is 6000X. We didn't put the 0X in front. These are all X addresses. Okay, and I don't recall what the data segment looks like too, but we could look that up if we needed. But you'll see that 6000X is something that will come up in today's class. Okay, but anyway, that's what we're eventually going to get to. How you put the data into this data segment, and that's one of the things you need to know in order to do software number 5. Okay, but where we're going to start first is with the alternative names and uses of the reg file registers, because up till now you've just been using like X0, X1, X2, and so on to X31 for the reg file registers. Okay, but starting with software number 5, which is the last software assignment other than there's a final project part, that's also software. So for software number 5 and also for the final project that deals with software, use the alternative names, okay? Instead of using the X, okay, you use the alternative name. So there are 5 special registers. Yeah, the first 5. I was wondering from that why I said the first year, but the first 5 registers, those are your special registers, right? So, X0 through X4. X0 we talked about, right? Because what's special about register 0 in the reg file?
Hardwired to 0.
Hardwired to 0. So what's its alternative name? 0. Very easy, right? Okay, then X1, what is its alternative name? One. Good guess based on, this, but it's not one. What is it? Yeah, RA or return address. RA stands for return address. And then how about register 2? Yeah, that's P staff. Now you'll see, we'll talk more about the return address register and also the stack register when we get to the stack segment, and also when we talk about how to do subroutines in assembly. Okay. Now there's 2 others, register 3 and register 4. One is a global pointer, I think. Is that global pointer? And what's the other one? It's like thread something. Yeah, those 2 we're not going to deal with in this class, so you don't have to worry about special registers 3 and 4. Okay. Now, also some of the non-special, if you will, registers are called different things. Some of them are called temporary registers, and as you may guess, temporary registers are for data that's not long-term. Not long-term. So things like counter values. Like when you have a loop and you want to count how many times you're in that loop. And also just, registers you're using for like intermediate calculation. Okay, and on that sheet, it lists, which are the temporary registers. You have temporary registers T0 through T6, so there's 7 of them. And like T0 is register 5. T1 would be register 6, T2 register 7, and then T3 would be like register 28, and it jumps up after that. But those are your temporary registers. Okay, and then you have the save registers, and that's for data that's long-term. So that's like for input data. What else? Like addresses. Oops. And results. Okay, so again, if you look on the sheet, you have what, 12 saved registers, S0 through S11. S0 is register 8, S1 is register 9, S2 is register 18, and so on. Okay. There's also what are called function arguments. Those are the A registers. Let's see, how many of those do we have? We have 8 of those, A0 through A7. This is when we get the subroutines that this becomes relevant. Okay, so we're gonna kind of just skip over it for now, and then when we talk about subroutines, we'll talk more about the argument registers. Okay. But you know, the reason why they kind of categorize these different registers is because it will make code like more mobile, if you will. You know, if people abide by this, then the programs, especially when subroutines are being used, are more like standardized, so to speak. You have a question?
What is the chapter immediate for the temporary?
Oh, calculation, sorry, I was abbreviating.
No, it's just harder to track here.
That's all right. Yeah, if I ever write something that's not clear, please let me know. Yeah, calculate, just like immediate calculations. So, like I said, for software number 5, instead of using like X5, X6, you know, you're gonna start using like T and S. Now, if you know, like in software number 5, if you know you're really using a temporary, or you're using a temporary register for temporary, or vice versa, you're not going to be marked down. Okay, so you know, when you do the final project software, which is going to involve a subroutine, then you're graded on whether you're using the right register for whatever whatever it should be used for. But for this software number 5, we want you to use temporary and save, but if you mix them up, we're not going to mark it up.
So temporary and save, those are designated, that's programmers, programmer's choice.
Right, when you're writing your assembly language program, yeah, if you've got a register that has this use, you're going to use a T register, and if it's this use, you're going to use an S. So it's when you're writing your assembly language. It's just another notation for what you've been doing. You know, instead of doing X5, you would put, what's X5 again? X5 is T0. It's the, you know, the 0th temporary register. And like I said, the reason behind this, I think, becomes clearer when you talk about like subroutines. Yeah.
But the register themselves are just registered.
Oh, yeah, yeah. You know, whether you call X0, X0 or 0, it's the same register. It's hardware 0. Yeah, so it's just like the name implies, it's just another name, right? Alternative name. Okay, so any questions up to this point? All right, the next thing to talk about is directives that we have in assembly. And these assembly directives, they're just directions to the assembler to do something, right? So it's not part of a program, like it's not an instruction. Okay, so it's not like part of your program. Okay, it's something the assembler takes other than you know, instructions in the program. So because it's not an instruction, it's also, it doesn't generate machine code. You know, like we talked about, like you've seen, you know, with your different assignments, right? In RARs, where you put the instructions for your program, right? And hit that assembler button, it's taking those instructions and converting it into all the 32-bit machine code instructions. Okay, well, that's not what a directive is. Okay, that doesn't happen with a directive. Okay. So let's go over some of the common ones that are good to know. The first one here is, this is a dot. So dot EQU, which stands for equivalent. That's how you can assign numbers to you know, words. Now, when it's a word like this as an assembler directive, it's not called a label like it is in the program. Right? You've written programs where, you know, instead of an immediate in an instruction, like a branch instruction, you put a word, which is called a label. Okay. This is actually called, when it's in a directive, this is called a symbol. Okay. So this directive, it will just assign whatever number you put here, like we put this address that, we have the switches, it just assigns this to this symbol switches. So, the advantage of doing something like this is that it would just make your code more readable, because now, you know how we were using the load immediate, like load immediate, and then you would have a register like maybe 20 now, instead of 5, and you would put the address, right? You would put this address here, and it would just load the address into this register. Well, if you had this directive before this, you could just put switches, right, instead of this number. Okay, so it makes it a little bit more readable. Okay. Now, .text. I'm putting the number sign because in RARs, right, when you make a comment, it's a number sign. .text, that's the default directive. And this is how you identify that what follows is code. Now, you haven't done this previously because you didn't know anything about directives, right? Because all you had was code, there was no reason to put this. Okay, but if you have, other directives, assembler directives, like in your program, well, you have to tell the assembler where your code starts. Okay, and .text, that tells the assembler that everything after that is an instruction. Okay. Okay, and then we get to this directive .data, and this is directive that tells the assembler that what follows has to do with the data segment of our real memory. And the default the default is that it will take the data as a word. But you can specify something else. If you wanted to take data as either a byte or a half word, you can specify. So this is the default. Word is the default. Okay, you can specify. And the way you would specify is you just put like .byte. It's .half if I remember it. It's .byte. Yeah, .half. And you can also put .word. Anyway, if you don't put anything, it's going to default to word. Okay. All right. So I think the best thing any questions up to this point? This is just kind of like definitions, and then we're going to do some examples with this coming up. So everybody good? Okay, so let's look at this first example here. So you can see I put the assembler directive data. Okay, and then after that, you can see here .byte with hex 23, .byte with 10, .half with hex 25, and then .word with 100. So just like you've seen in the RARs with the instructions, right? If you don't specify like a hex, it will just take it as a base 10. Same thing with the data directive here. If you don't put the 0x, it'll just take it as a base 10 number. But the main thing I wanted to point out here is that just like the code segment, the data segment is byte addressable. right? That's what allows us to make these, the non-default values of dot half and dot byte. So if you look at the data segment, just like the code segment, each 32 bits is divided into 4 bytes. So this first byte has address 6000. This next byte would have address 6001. Again, this is in hex. This would be 6002, 6003, right? Then go up to 6004 and so on. And so again, every 32 bits is separated by 4 in address. Okay, so the data segment, it's segmented the same as what the code segment is, right? The only difference is the code segment has instructions, the data segment, has data. So if you type this, right, you put dot data, and then you put this byte with this 23 hex data, it's putting this data, it's putting this 23 hex at address 00006,000. So you see, it would put that data, that 23 hex, right in this byte right here. Okay, and then it would put this byte, okay, this 10 here, it would put this at address 6001. Okay, so we put that 10 right in that part of the data segment. And now if we had half with this hex 25, now how many bits is a half again? 16, which is 2 bytes. So it would put it at address 6002, and it would take up these 2 bytes, right? With 16 bits. And then this word, right, this data 100, this word, well, it would be at address 6004. Actually, here in these 32 bits. Okay, so the data segment works, just like the code segment does. And as we talked about before, you can never cross word boundaries. So see, you wouldn't be able to put like a half word in the data segment at address 6003, because if you tried to do that, it would try to cross this word boundary, right? It tried to put a byte here and a byte here. And the way real memory is set up, the way it's designed, it doesn't allow for word boundaries, right? If you tried to do that, the assembler is not going to like it. Okay, just like it wouldn't like it if you tried to, have something in your code that crossed the word boundary, like you tried to do a load half word, you meet this address, the same thing would happen. Okay, so any question about, where I'm getting these addresses from and how it fits in with the picture over there? That's probably the key thing of understanding this. Okay, well, you can have what we call symbols, which are like labels in your data segment, right? They're called labels when they're part of your code, right? Like we've seen with the branch instruction and jump instructions and so on. But in the data segment, they're called symbols instead of labels. Okay, so that's why I'm using D_sim1, short for symbol. So you can have an example like this, where again, you start off with data, because that tells the assembler what follows is going to be in your data segment. And you can see here I have a label followed by a byte, another byte, half word, a word, and then I've got a second symbol where again I have a byte here. So again, if you were to look at the address, okay, so these are addresses. Okay, well this is going to be at address 6000. I'm not going to put all the zeros. Okay, so address 6000, I'm just put 0x. Maybe I should put the 0 sign. 0006000. I'll put it one time. But for all these others, we got all the zeros in front still. So just like we wrote up here, this byte would be at address 6,000, this next byte would be at address 6,001, then this half word is gonna be at 6,002, and then this word would be at 6,004. And then where would the address of this byte be for this symbol? Right, I heard it. What is it gonna be? Right, 6,008, because this word is at address 6,004, so it's taking up these 32 bits. Right, so the next address, right, that's available where you don't cross a word boundary would be 6,008. Okay, does everybody see that? Everybody agree? Okay, so the next thing is, well, how do you read from a data segment? And look, we have a new instruction that we haven't used yet. Okay, so this again is where it's handy to have an instruction set to look at. So if you go and you look at the instruction set and you look up this instruction LA, it's load absolute address of symbol. Okay, so like I said before, when you're dealing with the data segment, we call these symbols instead of labels. Okay, but they essentially act the same way. They just got different names. So you see what this instruction is going to do is that it's going to take the address of this symbol. So in this case, it's going to take this hex 6,008 and it's going to put it into register 5. And so you see this takes the address, puts address. So E underscore symbol into register 5. Question?
Yeah, isn't the address of DSIM1 at 6,004?
Oh, I made a mistake, didn't I? I was looking at 2. So this would put the address. Oh, no, wait, I wrote the right thing here, right? The symbol. So it's gonna take this address of 6,000 hex and put it into this register 5. Is that what you're asking, or?
Yeah, well, yeah. No, DSIM1 is just that.
Right, we're looking right here.
Okay, so it doesn't encapsulate all the next type.
No, it's just taking this address. Again, if you look at the instruction, the LA instruction, the pseudo instruction, it tells you what it's made out of, but then it says, let's see, where is this? Yeah, it just says, instruction loads the upper 20 bits of the address associated with the label. Now, I think that's a typo because if you look at the description for this instruction, in the form of the instruction, it has LA, then RD, right? This is RD, the destination register. And then it has symbol here. Okay, so even though in the detailed description, it refers to this as a label, it's really, again, a symbol. And again, the only difference between symbol and label, symbol refers to the data section as opposed to the code section, where we call it label. Okay, but if you read the description of the instruction, it's taking that address of this symbol and putting it in this register. So I think I know why you might have a question about, because when we use the LI instruction, right? Remember, load immediate, and you'd have like some register, and then you would have like, you put a number, and that number is the switch address, right? Where you see it's just taking this number. And when you use a load immediate, this doesn't have to be a number that's an address. It can be any number. Just so happens we use it this way because then we have the load command after it where, we're using that as an address. Okay, but this is a different instruction. It's not a load I instruction. It's a different instruction where it treats this as an address. Right? It puts that address into whatever register that you specify.
So it'll put the 6,000.
Right, exactly. Exactly, right. It's gonna take this hex 6,000, put it into register 5. And now we follow it with a load byte. And, this is just like what we would follow the load immediate, right? We have either a load word or a load half word load byte. So now what it does is it takes what's in register 5, right? The 6,000 hex, it's gonna add 1 to it, use it as an address, and it's gonna load, or it's gonna load the data, that address into register 6. So we loaded 6,000 into register 5. Now we're gonna add 1 to it, right? So now we're at address 6001. And now this data, this byte right here, will be loaded into register 6. Okay, so you see this instruction loads the content of data segment address 6001 into register 6. Right, so it's going to put that hex 20 into register 6, right? So we see like the contents 20 would be in register 6.
So OA will put the first address of the symbol in. I mean, DSIM1 has there are 4 instructions, there are 4 directives there, right? Each has its own address. So it's only going to put the very first one, each symbol.
Exactly, yeah. Yeah, because just like, in a code segment, like each instruction, each line has an address. Each line here has an address in the data segment. So, this date is at this address, this date is at this address, this date is at this address, and so on. Okay, any other questions?
Sorry, it also adds value as well, so it makes it.
Yeah, this is no different. We've seen this before. Like when we were doing the code segment, right? The only difference is we have a load I first instead of a load A. But yeah, whatever number you put in front of the parentheses, it's just going to add that to what's in the parentheses. So this is like that offset. You know how you would have it usually 0 when you're reading from the switches, but later on you'd put like a 40 in front of it, to output to the 7 segment. Yeah, it's the same type of structure. Any other questions? Okay, the next thing is how you can do arrays in assembly. And here, what we can use is a directive where you can basically allocate space in the data segment without putting a value in. Here with the data directive, like we're specifying, what data is going at a particular address in the data segment. Okay, but there might be cases where you just want to allocate some space in the data segment, and then maybe later on you'll store things into that segment. Okay, so if you essentially want to create like an area of the data segment where you don't initialize the data at the very beginning, you can use this directive here, .space. Okay. So what this means here, this .space with the 20, is that this 20 is bytes. So what this is going to do is allocate 20 bytes of the data segment without putting an initial value. Okay, and since it's the first line here, right, after our let's see, I don't think I put it directly, but we would have to have like a dot data. you have to have a dot data first. So what this will take is it will start at address 6,000 and then allocate 20 bytes. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. That's a lot.
Or it would just be like 5 addresses.
Well, 5 what addresses? I mean, you're right, 5 what addresses though? Because what are these? What are these addresses? The ones that are addressing 32 bits or what kind of addresses? Word addresses.
Yeah.
Yeah, so, yeah, you're exactly right, that 20 bytes would be 5 words. Okay, so, your word addresses, let's write it up here, word addresses. Okay, your first one's gonna be what? 6,000. Then we got 6,004. And then 6,008. Then
6,001.
6,000 what?
1 add.
It would be C, right? So it would be 12 and 12 is, or C is 12 and so 6,000 C. 60 what? 16. Right, because that's 16, well, the 6 and then 16. So those would be the 5 word addresses. So now if you follow this with another line here, where you're specifying the word. So, this like we said, this allocates, 20 bytes where we're not putting any data in initially. But now we could follow that with putting this word, right, this text 10 word, into the next address of our data segment. So what address would this be at? The address be 6,000, but what would follow this? 11. Well, 11, 6,000 is here. 6,004, 6,008, 6,003, 6,010, 6,011 would be here. Can we put a word at 6,011? That would cross a boundary, right? So what address would this word have to be at? Yeah, 14. And have to start. Have to be here, 6,014. Okay, and then we follow that with a byte. So what address would that byte be at? 6,018, right? Again, this takes up 32 bits, so this would have to be at the next word address, but it would just take up 1 byte.
Does that mean, well, like what's happening after, like in that little space that we have to skip over?
What are you putting in?
Like in the, so we can't really put a word at 6011. Right, because
Okay, so you're talking about over here that this has to be at 6,014.
right. So what happens from 6011 to the 6013? What's going in there? Nothing. Just
Well, if you look before this, see, we allocated this amount of space.
Yeah.
And 6,010.
oh, it covers the whole.
Yeah, and
Okay.
32 bit, it's, yeah, these 20 bytes are 5 words. So 1, 2, 3, 4, 5. This whole block here has been allocated without an initial value. And the next thing that's available is the 6,014. So yeah, if you somehow tried to put this at 6,011, Well, first, you wouldn't want to do that because again, if you're using the space directive,
Yeah.
that means, you don't want to put anything initial there. And even if you did put 6011 for a word, it would cross a word boundary.
Yeah.
And again, the assembler is not going to like that.
So what if like hypothetically you had like ignoring that whole like spacing, but like let's say you put a byte at like 6010,
Okay,
And
so a
then
byte at 6010.
but you wanted your next instruction to be a word. Then you have to put it at 6014, but what's gonna happen to 6011 to 6013?
Okay, so let me make sure. So let's see, 6008, 2000. So you're talking about like this byte right here,
Oh, sorry.
6010.
Um. Actually, look, okay, sorry, 6008. If you put a byte at 6008,
Okay, put a byte here.
and then
Now
your
what?
next thing had to be a word.
Oh yeah, the next thing had to be a word. It couldn't go here. It couldn't
Yeah.
go to address
So it would have to
6000.
go to 6000C.
Yes,
But what's gonna happen to 6009 to?
and we're not talking about allocating space. We're just talking about
Right,
putting,
it's just like,
there's gonna be some data there, but you're not gonna know what it is.
okay,
So you probably best not to address that, right? Because it would be like Russian roulette, right? I mean, it could, it could cause your program to go haywire because you're not gonna know what's there.
so it's probably
Like you
best.
can't, like if they're just like in the code segment, you can't assume that, like memory is gonna be zero
So it would
unless you
probably,
initialize.
so it would probably be safe, this is just allocate space in that little area and then keyword.
That's a good question. Like, how do you safely,
Save them in those little section.
probably the best thing to do is, put something there that you know the value of, right? So if by some chance your program goes there, you at least know what's there. So maybe you would want to initialize it just to 0.
So,
Hey, there's questions here.
so if you set the byte, the value, it wouldn't just set the last bytes, Like,
No, you can't count on that. No, that's a good question. Like, say you allocate the space and then you like store a byte at one of these, all you know for sure is that that byte has that value that you stored there. Whether it's a store byte or a load byte, those instructions only are concerned with the byte. It doesn't know anything about the other bits like in that row. Yeah. Yeah, so it doesn't initialize or anything. Yeah, you would have to make that happen. Like with another instruction. Yeah, that's probably one of the most common, common things that come up that causes programs not to work the way you want them to work is that people make assumptions that there's gonna be like a value there that gets overwritten, or they think because, that part of the memory or data segment wasn't used, that it's all zeros, but you don't know. The only thing you know is that there's data there. There's zeros and ones there, but you don't know the zeros and ones unless you make it the zeros and ones you want. Okay, just a few more things and we can talk specifically about software 5. So the next thing here is, creating arrays in assembly and then loading from an array. So again, I have another example. So you start out with the data directive. So here, this is again going to allocate 20 bytes of the data segment without specifying initial value. And then it's followed by, we're actually specifying data in the second array. You can see here. Now, instead of writing like dot byte, you can do this. You can put dot byte and then separate what you want. Well, actually, let's actually do the addresses here just to hopefully make it clear. So again, if we look at the addresses, this is 20 bytes again. So we have, like we said before, these 5 addresses, right? 6,000, 6,004, 6,008, 6,000C, and 6,010. So now if we follow that with this array and we rewrite the byte data out this way, well, this 3, see, I'll write it over here. The 3 would be at address 6001 or 6011. Okay, and then the 7 would be at address 6012. Right, and then this 8 would be at address 6013. Everybody agree with that? You see how I did that? Okay, all right, so this is just, again, allocating 20 bytes or 5 words where we're not initializing the data, and it's following it with 3 bytes where we are specifying what the data has to be at those addresses. Okay, so that's just putting the data in the data segment. Question?
Should I take the first 5 be at 6014? That's,
Oh, you're right, because this is a word. Oh, yeah, thank you. Very good. Everybody see the mistake I made? Does everybody see why that was a mistake? Because this last word, 6010, it's 32 bits. So it's taking up 1, 2, 3, 4 here. So 6014 is where that byte can go. So thank you for the correction. Okay, so now does it make sense? Okay, so this part is just putting, data into the data segment along with allocating some reserved space, if you will, that we're not initializing. Now comes the code, right? Now comes the loading. So again, you didn't have to do this previously because you never had like a directive, right? All you were doing in RARs was putting in instructions. So you never had to tell it the text. But now since we've got like this section that's, data, we now have to tell the assembler, hey, now what follows our instructions, right? So again, the dot text tells the assembler that what follows our instructions. Okay, so we use this load absolute, and it's going to take the address of array 2, the address of array 2, right, which would be the 6014, and it's going to put it into register S0. And that's the alternative name, right? Say register 0. What's the non-alternative name of S0? Like what register is that? What number? Right, that's register 8, right? So if when I'm pretty sure in RARs, let's see, does RARs have the alternative names? Does anyone? Do they have the alternative? Okay, yeah. I was trying to think. I've used the text, the non-alternative so much. So I guess RARs does have the alternative names in there, in addition to the non-alternative. All right, and then we use another LA command that's just going to put the address of the other array into a different register. I can put into register S1. Right, so that would take address 6000 and put it into this register. Okay, and then we're following it with the load command. So we have a load byte here. So this is the destination register. All these are RD. Okay, so what is this part of this load byte instruction going to do? Actually, maybe we put the address here. See, this is address. See, this is array 2, so this is address 6014. This is address 6000. So, what does this part of this instruction do? This one in front and in parentheses here, right? We put address 6014 into register S0. So now what's this?
adds.
Yeah, it's just going to take one, add it to what's in this register, which is 6014. So now we're gonna have address 6015. It's gonna take the byte at that address and put it into register T0. Right, so you see this puts byte at address 6015 into register T0. Everybody see that? All right, well, if that made sense, what's this doing?
Adds it to,
Nothing. That's 8
to the address. And then
right, adds 8 to this address 6008, and then it takes the word at that address and puts it into this destination register, right? So, you know, this puts the word at address 6008 into register T1. So what would happen, do you think, if instead of an 8, that was say like 6? What do you think would happen when you go to assemble that in bars? What's that? Yeah, it won't like it. Why won't it like it? Because what is it gonna try to do if you use this address here for a word address? It's gonna try to cross a word boundary. Right? See, this would have to be, whatever number you put here when you're using a load word, this would have to be divisible by 4. Right? Any number here not divisible by 4 is gonna cause a problem. All right, so with that, you should be able to work on software number 5. Now, software number 5 has 2 parts, just like the other software assignments have had. And unlike the other software assignments where I would do one in class and then have you do the other one, this one here, I'm just going to give you a head start on the one that you have to do. I'm not going to do a full example, and the reason for that is the second part of this. So you're going to do part 1, and I'm just going to start it out for you. But part 2, if you look, question. Oh, thank you. It's amazing how I can never remember that, right? And I have the thing up there, and I can never do it. There we go. Need some WD-40 for this. Rotating in the time. So anyway, if you look at the second part of the software number 5, it has to do with sorting. It's basically a sorting problem. And the reason why I'm skipping over that is because, in my judgment, based on what software language that you knew or know before this class, it kind of makes an uneven playing field, because really to do that problem, if someone knows the C programming language, you can just take any sort of algorithm, you know, for sorting, especially if it's C, and it's not that difficult to do, to take that and then go to assembly. But I do realize that especially like EE students, unless you took that special 1-unit class that they offer, you probably haven't had any C at all. So anyway, I've decided just to skip over that sorting problem. Now, when you do your final project software, you know, you could do it as a final project if you wanted to. Yeah. But anyway, we're going to skip over that one. So I'm just going to start you off on the part that you have to do, part 1. And this is the problem statement. You know, using the data directive that we just talked about, define an array in the data segment that contains the first 25 values of value. Oh, I had to look this up on Google. It's the last name of a mathematician. Does anyone know how to pronounce that name? Is this right? Fibonacci? Fibonacci. Because it does not look like, when you look at how it's spelled, I would have never guessed it's pronounced this way. So Anyway, supposedly this is a famous sequence. Tell you the truth, the first I heard of it was when I looked at this problem, but I guess like in the computer science world. And also like in business, I guess they use this sequence and. Maybe it's to figure out this stuff. But anyway, there's this sequence and. Basically, it's a sequence where you're taking two numbers, adding them together. And just successfully doing that kind of thing. So anyway, you take the first 25 values of this sequence, and if you want to see the sequence, just Google it. But you want to start at 0, and you just want to go up to this number here. I mean, I guess it goes on to infinity, but we're just going the first 25. So you're just going from 0 to this one. So you've got to put this sequence into the data segment first. That's what I'm going to help you with. And then after that, it just becomes writing a program where you're going to process through that array, take two values that are 3 spots away, take the difference of those two values, and output the difference to get LEDs. Okay. So to get started with this, you would just put the directive dot data. And then you could just put a symbol. Now, just like with labels, symbols in the data segment, they can be anything you want, so you can make them descriptive. So for example, I use sequence. We're talking about a sequence. And then specify a word. And then you can just go ahead and just list this sequence, which again, if you Google it, you can get the sequence. So, you start out with 0, 1, you add these two together, 1, then you add these two together, 2, add those two together, 3, add these two together, 5, add those two together, 8. You just keep going. Like I said, you can Google it, or you can work it out yourself. But after you work it out yourself, you might want to check to just make sure you get the right values. But you're going to put, the first 25 numbers of that sequence. And this will put it into the data segment starting at address 6000. And since this is defined as words, it's just going to be word addresses, right? You have, this would be at address 6000, 6004, 6008. 6000 C, right, and so on. Okay, so that's the part I'm going to give you, is just how you set up the array in the data segment. Then, right, you put .text because that tells the assembler now what follows is your program, are your instructions. So this is what you got to figure out, right, to make this happen. Okay. All right, so do you have any questions? Because the rest of the time, well, remember, tomorrow, the ALU and the immediate generator are due. So if you don't have that done, that should be your priority. After that, the priority should be your branch condition generator and your branch address generator, because that's due Friday of this week. This is due Tuesday. The reason it's due Tuesday and not Monday is because Monday of next week's a holiday. Okay, so this is due Tuesday, the 21st.